Hi students, welcome to Practical Science. This is episode 4 and today we're going to have a look at elephant's toothpaste. So today what I thought we'd do is start having a look at some of the common substances that we have around that you can purchase from the shops and to start to look at some of the chemistry behind these. This is a particular product which is very good if you want to bleach your hair, but it contains the chemical peroxide. Now I know by looking at this there's a 9% value here. This 9% means that this is not pure peroxide, but there is 9% of this. Hydrogen peroxide is a really important compound, not just if you want to bleach your hair, but also to create one of the most well-known experiments that high school students in particular love to do, and that is the elephant's toothpaste experiment. So we're going to do that today, but we're also going to look at some of the chemistry behind the elephant toothpaste experiment, and we're going to investigate the effect of concentration on reaction rate. This means we're going to move across a little away from the type of reaction, which is a decomposition reaction, into an area of chemistry, a physical chemistry, known as chemical kinetics. Chemical kinetics is basically a branch of chemistry where we look at the energy associated with chemical reactions and the factors associated with the rate of chemical reactions. We're going to see if we can vary some of the conditions for this particular experiment and see if it makes a change in how the reaction proceeds. To do that, we're going to be recording starting and final temperatures. Because we're recording, we're also going to have a timestamp so we can check the rate of these reactions in terms of time. And we're also going to measure out different amounts of peroxide and also water, so I'm going to dilute that concentration a little bit to just see if the change in concentration has an impact on the reaction rate. So the first thing that we need to do is we need to collect some of this peroxide. So I'm going to just put in 3 mils for now. Okay, we're going to do a test run first of all, just to see how this reaction is proceeding. So I'm going to transfer that to the beaker. In the classic elephant toothpaste experiment, what we usually do is add a little bit of detergent. So detergent holds the bubbles together, the bubbles of oxygen gas together. And sometimes we'll also add some food coloring, which just changes the color a little bit. So you can do that if you wish. This is a decomposition reaction, and it's actually happening right now. One of the problems with some types of reactions is that the reaction rates are very slow. Hydrogen peroxide, which has the chemical formula H2O2, decomposes into oxygen gas, O2, and water, H2O. And it's doing that now, but it's very, very slow. So one of the ways that we have for speeding up a chemical reaction is to add a catalyst. This is manganese dioxide, MnO2. Manganese dioxide catalyzes this reaction. At least we hope it will. Let's add a little bit. So I'm going to get my spatula. I'm going to get just a small amount, kind of a level spatula full, and we'll pop that in there. just going to see
Do you want me to back up?
if there's any
Back up and get
difference
this.
in the temperature. Wow, look at that. Okay, so now we know that the elephant toothpaste experiment works. It's a little slower, and I'm going to just change some things initially. This is one of the reasons why we test our experiments first of all. I've realized that I've got too much of the catalyst in there. You can see the black color, which is the manganese dioxide, kind of dominates this. The oxygen that's being produced is coming through, and it's pushing basically the foam out of the way. I think one of the things that we want to do is we want to dilute this a little bit. So I'm going to make a series of dilutions. So I'm going to start with my initial 3 mils of the peroxide, but I'm going to add 2 mils of distilled water. That's going to bring me up to a final volume of 5 mils. I'm going to then successively dilute, so I'm going to use 3 mils, 2.5 with 2.5 water. We're going to have a look at the reactions for all of those as we work through, and we're going to do one more thing. We're going to use our temperature probe, and we're going to see if we can identify the change in temperature as these reactions proceed. 2 final things to talk about. Firstly, I'm going to go with the conical flasks because they look a little bit more impressive when they're coming through from the conical flasks. And finally, I am going to see if I can test for the oxygen. Now, we can see that there's obviously some gas in there that's pushing all of that foam out of the way, but we don't know that it's oxygen. I mean, you can believe me, but it's better if we test for it. So we're going to try and use the glowing splint test, which means that if I can light my little piece of wooden taper and I blow it out, I'll get it to glow red. If it goes into a sufficient amount of oxygen, then that may be enough for it to catch fire again. The foam here is really thick, so I did try this initially and all it did was put it out. But we'll actually see if we can identify positively that the gas is oxygen. Let's measure the starting temperature. So that's still coming. Pretty good. All right. Time for our second trial. See, the glowing is the oxygen that's in there. It's a small amount of oxygen that's being produced because it's a small reaction, but it's definitely, can't quite relight it, but it's definitely giving me a nice little glow there. That's the oxygen that's being produced in this reaction. So whenever we see bubbles, we always want to test those bubbles to see what we've got. Elephant toothpaste, a decomposition reaction where the hydrogen peroxide decomposes into oxygen gas and water. It's an exothermic reaction. We now know that it's an exothermic reaction because we saw the temperature rise, which means heat is being given out in the reaction. We also saw a difference in the concentration. We saw a fast initial reaction from the lower concentration, and that was basically because the water had pulled some of those peroxide molecules apart from one another, and we were getting them in contact with the catalyst, which was allowing them to catalyze that reaction. But then the fact that there were less of them, and that's what concentration's about. It's the average number of particles in a space. So we calculate concentration by the number of particles, or more precisely, the number of moles divided by the volume. And so if there's less moles in there, then there is less moles to react. And so the reaction slows down and we don't get quite as much of the foam that's produced in the lower concentration as we did with the higher concentration. We've also tried to control some variables in this experiment. We've tried to keep the amount of volume of the two solutions the same, so just changing the amount of, or at least a proportion of the peroxide to distilled water. We've also tried to keep the amount of catalyst the same as we've sought to see what effect the concentration has. So therefore we've tried to keep the catalyst the same so it does not become a factor in this reaction. You can see if we add some detergent, we'll pull the gas bubbles a little bit further apart, they'll hold together a little bit better, and perhaps the oxygen test might be a little bit more conclusive, but you could see the oxygen was making those that red glow a little bit more. We know that fire requires oxygen in order for it to continue and to burn, and so that oxygen that's being produced here was having that effect. The important thing, of course, is that we make sure that we don't douse our flame in this quite thick foam that's been produced as a result of this experiment. So this is a decomposition experiment, one reactant producing two or more products. One of those products is a gas, the gas oxygen, and that's what creates this foam, all those spaces in there filled in by the gas that's being generated in this reaction. And the fact that the temperature went up tells us that it's an exothermic reaction. Definitely one to try, and not a bad result for a hair care product. Thanks for watching.